So in this video, we're going to take a look at problems 1 through 15, which is in the module 6-7 section over radicals. So the way that this is going to work is I'm going to show you how to do one of the problem types. Then you can pause the video, try the problems, and then resume to check your work. These are all review. You shouldn't need to know how to be shown every single one because we've learned this prior. You also have additional videos from those modules when we took those assessments previously in the semester. So again, I will show you how to do one, and then you will work through the additional problems. So on number 1, we are simplifying the cube root of 162x to the 7th. So on 162, we're going to start by breaking that down into its factors. 162 breaks out into 2 and 81, 81 into 9 and 9, and 9 each into 3 and 3. Whatever the index is of the problem is what we're looking for in terms of groups. So I have this group of 3s, but 2 values left behind. So I bring out a 3 and leave behind the cube root of 6, because 3 times 2 is 6. And then on x to the 7th, I'm going to divide it by 3. 3 goes into 7 2 times, so I'm going to bring out x squared. And there's 1 left over. So remainder 1, so x to the first stays in. So at this point, go ahead and pause the video, try problems 2 and 3, and then go ahead and resume to check your work. And here was the final answer on number 1. At this point, go ahead and take a look at problems 2 and 3. Number 2, we got 5ab, square root of 5a. Notice that on number 2, there was no index listed. If there's nothing listed, we assume it's a 2. So onto the variables. We divide each by 2. For the a's, 2 goes into 3 one time, so we bring out an a and we leave 1 behind. For the b's, 2 goes into 2 one time evenly, so that's all we're bringing out. On the number part, I can't make this a group of 5 or a group of 3 5s because I'm looking for 2. So I have one group that comes out and one that stays behind. On number 3, our answer is 14xyz, square root of 2yz rather. Again, index was 2. On the number part, I broke down 392 into 2 and 196. 196 breaks into 14 and 14. At that point, once I see a pair of 14s, I don't have to break it down any further. If I did break 14 into 2 and 7 for each one, I would get the same thing at the end, but I noticed that it's already a perfect square that I can bring out front. So now we're taking a look at 4, 5, and 6. 4, 5, and 6, they're all multiplication problems, which will turn into problems like we saw above in the regular simplifying ones once we multiply. So when I multiply these two radicals together, I get the cube root. 12 times 16 gives me 192 of b to the 5th. As I look now at cube root of 192 b to the 5th, it's the same process that we saw above. So I'm going to go ahead and break 192 into its factors. 192, when we know it, if I didn't know where to start, I just multiplied 12 and 16 to get there. So that's probably a good starting point. 12 can be 3 and 4, and 16 can be 4 and 4. So notice how I'm strategically picking numbers that maybe I don't have to break down completely, but still give me that group of 3. So I'm going to bring out those 4s and leave behind the 3. And then I'm going to move over to the b's. I'm going to divide them by 3. 3 goes into 5 one time with 2 left over. So our answer is 4b, cube root of 3b squared. At this point, you should go ahead and pause the video, try problems 5 and 6, and then resume to check your answers. So taking a look at 5 and 6, notice that 5 and 6, they both have coefficients out in front of the radicals. So on number 5, I had a -2 here. When I multiply the radicals together, I carry that -2 with me. We were able to bring out a 5. So again, we are looking for groups of 2 here. So that was a -2. Let's make sure we get that. When I take out that 5, I get to multiply it by the -2 to give me -10. Otherwise, the problem is pretty much the same. On number 6, it was the same concept. When I multiplied those two radicals together, -4 times 5 gives me -20. I'm then taking the fourth root of 2048 m to the 9th. Again, I strategically pick numbers maybe bigger than 2, although if you broke it down by 2s, that would work as well, because I know that I wouldn't have to be doing quite as much work. So I was able to get a group of 4s to bring out front with 8 left behind. I then divided 9 by 4. 4 goes into 9 2 times with 1 left over. Now we're on to converting forms. I'll go ahead and go through all of these with you because these are pretty quick. They give you a guide here. So whether we're going from radical to exponential, or a rational exponent to a rational exponent back to radical form. So this one's in rational exponent form. So I need to have a radical. 7's the base. Whatever the denominator is, that's the index, and we take it to the 4th power. So that's all we're doing, converting forms back and forth. The second one, I need a radical. B is the base. 4 is the index, and 7 is the exponent. On number 9, we're going the opposite direction, where I'm needing to write this with a rational exponent. X in the base. X is the base. 3 is the exponent. 2, even though it's not written, is the index. So now let's go ahead and take a look at the next page. We're on to 10 through 15, which are all solving questions. With you, I'm going to go through 10 and 11, and then you're going to pause the video, try them out, and then you can resume to check your responses. Our goal on radical equations is to start by getting the radical isolated. Then we can go ahead and raise each side to a power. So I'm going to start by dividing by 8 on both sides. So I'm left with square root of 4r equals 2. I then raise each side to the 2nd power. All of these are square roots. That means they have 2 as the index. That's why we're raising it to a power of 2. But if I had something else as the index, let's say I had a cube root problem, I would raise it to the 3rd power. So I'm left with 4r equals 4. And then to get r by itself, I divide both sides by 4. So for number 10, r is equal to 1. On number 11, we're going to notice that we have a radical equal to another radical. Even easier, if I have 2 of the same radical, I just raise them to the power. It's kind of like I'm just setting what's underneath the radical equal to each other. And then this is an equation that I can solve. So if I were solving this one, I would start by, let's subtract 2v on both sides. So those will get rid of the v's on this side. And then I'm also going to add 2 over here. So I'm going to be left with -3v equals 24. I then divide both sides by -3 so that I get v is equal to -8. At this point, go ahead and pause the video. Try problems 12 through 15, which are very similar to number 10, and then resume to check your work. So here are the answers for 12 through 15. Number 12, we had to add 10. Then we could square both sides to get our solution. N is equal to 64. On number 13, we had to add 8 before we squared both sides. So we were left with 36 equals 4k minus 4. And then to solve, we add 4, divide by 4 to get 10. Number 14, that was set up and ready to go. We went ahead and squared both sides. So we got x minus 8 equals 25. We then add 8 on both sides to get our solution of 33. From there, we move on to number 15. On number 15, we had 2 steps to take before we were able to square both sides. We start by subtracting 4. Then we divide by 8 to get 4 equals square root of 3v minus 5. Then we're able to square both sides, so we get the equation 16 equals 3v minus 5. And then the 2 steps we need to get v by itself are to add 5 and divide by 3 to get our solution of 7. So that covers module 6-7 in your review. If you still need additional guidance on how to get a little bit more information on how to solve problems in Module 6-7, my suggestion to you would be that on your Schoology page for review, you have these links that will take you back to the original module where we learn this information. So if I click on Module 6-7, I'm taken to the review that we did in this section. And if I click on the review video, I have an entire video on how to do more of these problems specifically. And that would be a huge help as well. At this point, hopefully you're done with Module 6-7 and you can continue on in Module 8, 9, 10. Now we're moving on into the exponentials and logs unit for Module 8, 9, 10. We're starting off by graphing exponential growth or decay functions. We're going to do number 16 as a class. So in the video, we're going to go ahead and do number 17. The first thing that I would do for a problem like this, where I'm graphing, would be to look at whatever horizontal translation they give us. That's going to dictate what I fill into my table. So horizontal translations always move the opposite of what the number tells us. So I'm going to fill in -1 and then go 2 less and 2 more than the number that they give me. Now I'm going to evaluate for those points. So that means I take -3, for example, and put in for x. When I put in -3, I get 1, then -1, -2, -2.5, and -2.75. Now I can go ahead and graph those. So -3, 1, -2, -1, and so on. And we can see our graph is coming together and looks something like this. We can see that it starts to level off there. This would be an example of exponential decay. The domain of this function is all real numbers, so -infinity to infinity. I can substitute any x value in to get any possible y value. The range, notice how it starts to level out. It's going to start at -3 and go to infinity. So wherever it starts to level off, that's your starting point. Notice that I have parentheses and not a bracket because -3 does not exist in the set of y values. We do have an x-intercept. We're probably going to have to estimate it here. It's somewhere between -2 and -3. So maybe let's say negative, I don't know, 2.75, 0. I don't have that point in my table, so we would have to estimate it. I do, however, have the y-intercept, which is 0, -2.5. We're never increasing. Okay, this function is only ever decreasing. We look at increasing and decreasing from left to right, and then we're decreasing from -infinity to infinity. Our horizontal asymptote, we can see that this function approaches -3, and that's in the function as well. So whatever that vertical translation is, that's your horizontal asymptote. They always start with y equals, then -3. This function has 2 transformations applied to it. We have a horizontal translation that moves my function not 5, but 1 unit left. And then this -3 is a vertical translation, 3 units down. And finally, we have the end behavior. As x approaches infinity means what's happening on the right side of the graph. So what happens to the y values as the x values get bigger? This one, our y values would approach -3. We can see that that -3 continues to pop up, so be on the lookout for that as well. As x approaches -infinity means what's happening on the left side, and we can see that those are going up to infinity. The last thing that I want to talk about for this function is any potential stretch or shrink. Sometimes we call those dilations that you would have on the graph. So let's say I put a +2 in front. That would be a vertical stretch by a factor of 2. So be on the lookout for that. Let's say I had 1/3 in front. That would be a vertical compression. It would shrink the graph by a factor of 1/3. If you were interested in what graph 16 looked like, obviously we went through this one in class, but you can see that this one would be considered exponential growth because it is getting larger from left to right. And you can see the key features there as well. So in the solving section, we have 3 different types of solving that we're hitting. We're solving by getting like bases, and then we're solving by converting forms, both from exponential to log and log to exponential. So we're going to start with number 18, and then I'm going to stop my screen record, do number 19. While I do that, you should be trying it as well and then resuming to see if you are correct. My goal when I solve by getting like bases is to get like bases so that I can then set my exponents equal. So I can make 64 be base 4. So if I have 4 to the 2n plus 2, I'm going to change 64 to be 4 to the third, because 4 to the third is equal to 64. And then n minus 2, I'm going to put up there in parentheses. Now that my bases are the same, all I'm doing is setting my exponents equal. So I have 2n plus 2, and I'm going to set it equal to 3n minus 6. Notice how I distributed the 3 through the parentheses. To solve for n, I'm going to subtract 2n on both sides, as well as add 6. I'm going to do this. Let me get rid of that. All right. And add 6. So that I'm left with 8 equals n. So at this point, you should pause the video, try number 19, and then resume to check your work. So the answer for number 19 is -1/6. So for this one, I had to change both 27 and 243 to be base 3. So 3 to the third is 27, and 3 to the fifth is 243. I then set their exponents equal and solve for r. On to number 20. This one we are solving by converting to log form. We have to get this part by itself. So we're going to start by adding 9. So I have 10 to the n minus 4 equals 67. Now I know that I can only do convert by log form, like solve by converting to log form, because I cannot get 10 and 67 to have the same base. So this is going to be log base 10 of 67 equals n minus 4. Log base 10 of 67 is something that you're going to evaluate on your calculator by typing log 67 divided by log 10. That's how we do change of base to get an approximation of that log. It's going to be a decimal, and that's okay. So log 67 divided by log 10, and I'm going to round it to 1.83 equals n minus 4. I then add 4 on both sides. So n is equal to 5.83. Now go ahead, pause the video, try number 21, and then resume to check your work. The answer for number 21 is -1.9. So this one I had a couple steps to take before I could convert to log form. I had to add the 8, then divide by -3. When I evaluated the log, I got 2.81. I then added 1 and divided by -2. For number 22, this one is solving by converting to exponential form. My goal is to get the log by itself before I can convert form. So to do that, I start by adding 8. So -7 log base 5 of 6x minus 5 equals -28. I then have to divide by -7 so that I'm left with log base 5 of 6x minus 5 equals 4. I then convert to exponential form where my base is 5, my exponent is 4, and it's equal to 6x minus 5. 5 to the fourth gives me 625. And then I need 2 steps to get x by itself. I would first add 5, then divide by 6. So 625 plus 5 is 630 divided by 6. That gives me 105. So at this point, go ahead and pause the video, try number 23, and then resume to check your work. For number 23, we start off by dividing by 2, and then we were able to convert to exponential form. Our answer was 1737. Moving on to the next section, we are expanding and condensing. So if you know how to do one or the other, you kind of know how to do the rest of them. So I'm going to do one of each type. and then we'll resume to check the entire thing. So our goal on expand is to take one log and make it multiple. So each variable or number gets its own log. So this is going to be log base 2 of a squared minus log base 2 of b to the third. The a squared is a positive log. The b cubed is a negative log because it came from the denominator. The last thing that I do is take my exponents and I put them as coefficients out in front of the logs. So this is 2 log base 2 of a minus 3 log base 2 of b. So my goal in expand, again, is to take one log and make it multiple. Now when I move on to condense, my goal is to make multiple logs into one log. We start in reverse. So my first step is going to be to move the exponents back onto the variables that they came from. So this is going to be log of u to the fifth minus log of v squared. Now I'm going to put it back together as a single log with u to the fifth on top and v squared in the denominator because that log was negative. At this point, go ahead and pause the video, try the remaining questions in this section, and then resume to check your work. So here are the answers for 25, 26, and then 28 and 29. So what I do want to point out in 26 and 29 was the fact that we had a square root of u and a 1/2 that we had to address. Now the 1/2, that we just throw back onto the z like normal. It's z to the 1/2. Even though it's a fraction, it still becomes the exponent of that z. I could convert it to square root of z because those are equivalent. More importantly, though, we have to know that square root of u or square root of anything is equivalent to u to the 1/2 or that term to the 1/2, which is definitely a question that you're going to see on your final. So if it was the cube root of u, it would be u to the 1/3, for example. So that is an important fact that we need to point out. At this point, that should cover this section. By today, it is Friday when you should be working on this section. You should have gotten through module 6, 7 yesterday, module 8, 9, 10 today. So you only have 2 sections left as we head into next week. On to module 11-12, which is our rationals module. As a reminder, our rationals module is a lot of factoring. So you have to know how to do those skills with factoring in order to be successful. I'm going to pick out maybe 2 of these to go through, but otherwise, finals review of factoring, that's going to be something that you're going to have to take some responsibility for as you review, because over the course of this entire school year, we have done tons of factoring. So if those are some methods that you need a little bit of help with, that's something that you need to review on your own. But I'm going to pick out a couple. I'm going to do number 31 and number 34. So number 31, they have a GCF in common that I would need to factor out. That GCF is 3. Let me get the right pen here. So I'm going to take out that 3. Left over is x squared plus 2x. And then negative 144 divided by 3 gives me negative 48. So on the inside of the parentheses, that's going to be x method. That means I'm looking for numbers that multiply to be negative 48, that add to be 2. Remember, GCF is something that we have to check for every time. So negative 48 on top, 2 on the bottom. The numbers that would work are 8 and negative 6. So I would have 3 times x plus 8, x minus 6, and I would be good to go. Notice that none of these problems have equal signs. They are not solving. They are simply factoring. I'm going to do number 34 as well. On number 34, I also have a GCF, which is 2. Left over is x squared minus 16. X squared minus 16, that's difference of squares factoring. So that factors into x plus 4 and x minus 4. Notice 4 is the square root of 16. So that's our answer for that one. At this point, I would go ahead and pause the video, try the remaining factoring ones, and then resume to check your work. So here are the remaining answers for the additional factoring problems. I went ahead as well and labeled each one with the method that you would use. Notice that number 33, that was also X method. Don't forget to multiply your A and C values together. But after you did that, you had to divide and slide. And then number 35, because it is 4 terms, that indicates that we're doing grouping, which means I split it down the middle and look for a GCF on each side. In this section, we're taking a look at simplifying, multiplying, dividing, and then adding and subtracting. I will go through one of each type, and I will periodically pause so that you can check your work. I'm going to go ahead and do number 37 for you. This is a simplifying problem. There's no equal sign, which means I'm going to factor the numerator, I'm going to factor the denominator, I'm going to see what will reduce. In the numerator, 4 is the GCF, so I'm going to take out that 4. Left over is an x plus 6. In the denominator, I've got X method, where I'd be looking for numbers that multiply to be negative 24, that add to be 2. Those numbers are 6 and negative 4. So I'm going to have x plus 6 and x minus 4. Now, at this point, it's probably best to list our restrictions. For this one, x cannot be equal to negative 6 or positive 4. I got those from flipping the signs of the terms in the denominator. So it's essentially values that I would substitute back in for x that would make my denominator 0, because remember, we cannot divide by 0. And even though this x plus 6 will cancel out, that term still gives us a restriction. So my answer is 4 over x minus 4. And I'm not able to reduce those 4s out. So 4 over x minus 4. At this point, I'm going to go ahead and try number 36 and then go ahead and resume to check your work. Is x plus 10 with the restriction, x cannot be negative 1. Now let's go ahead and take a look at, we'll do number 38 for this one. This is a multiplying problem, which really just means that I need to make this one big fraction. There's no need to find a common denominator. I factor all that I can factor and I see what will reduce. M plus 6, I can't do anything with, so I'm going to keep it as a factor m plus 6. Then I'm going to move over to this denominator. M squared plus 8m plus 12, that's X method. Factors of 12 that add to be 8 are 6 and 2, so m plus 6, m plus 2. I'm going to work my way back up to the top. We've got a GCF here, which is 9, so I'm going to take out a 9. Left over should be m plus 2. In the denominator, that 3m, we can't do anything with it, so we're going to keep it 3m. Okay, so from here, I'm going to list restrictions so that I don't forget about them. For this one, m cannot be negative 6, negative 2, or 0. Notice that this 3 has nothing to do with restrictions. It's the m that gives us 0. So now I can reduce stuff. M plus 6 will go away. M plus 2 will go away. So I'm left with 9 over 3m. 9 and 3 can reduce to be 3 over m. I will go ahead and jump in and do one of the division problems as well, because those are very similar, before I take a pause and let you try some out. So number 40 will turn into a problem exactly like number 38 once we flip the second fraction and multiply. That's how we divide fractions. So this is really 6 over x squared minus x minus 2 times x squared minus x minus 2 all over 2. So now I make it the same thing as I did on number 38, one big fraction where I bring down all of the factors. So 6 doesn't have anything that it reduces with, so that one stays. I'm going to move on to the denominator. I'm looking for numbers that multiply to be negative 2, that add to be negative 1. That should be x plus 1 and x minus 2. I'm going to move over to the top right. That's the same one. So I'm going to have, again, x plus 1, x minus 2. And then finally, this 2 gets to stay. I'm going to list my restrictions for this one. X cannot be equal to negative 1 or 2. This 2 in purple has nothing to do with any restrictions. The x plus 1s will cancel. The x minus 2s will cancel. And finally, I'm left with 6 over 2, which will reduce to be 3. So at this point, I would go ahead and pause the video, check your work on, try your work for number 39 and 41, and then we will resume to check our work and talk about addition and subtraction. So here's the work for 39 and 41. For number 39, our answer was x minus 6 over 8x squared with two restrictions of 0 and -3. On number 41, it was division. So again, I had to flip and multiply. I did all of my factoring, and my answer was 9x times x plus 7. Notice that I did have a 1 left over in the denominator, but dividing by 1 doesn't change what we have. So now let's take a look at addition and subtraction. In general, on addition and subtraction, we need to have a common denominator. So, for example, on number 44, I would need to factor the denominator that I have to see what they have in common already and see what the other one needs. I'm going to do number 42, though, so that we can get some practice on just finding that common denominator. Notice how neither of these denominators are the same. They have nothing in common. So I have to multiply by the opposite one. So the first one, I need to multiply by 4k plus 5 over 4k plus 5. And then the denominator on the right side, excuse me, and the denominator on the right side, I've got to multiply by 6 over 6 to get them to be the same. So then I'm going to go ahead and write this as one big fraction with 6 and 4k plus 5 as my common denominator. And then I'm going to write all of my terms across the top. I've got to distribute the 5 through. So I get 20k plus 25. And then I also have to distribute this 6. So plus 24k plus 30. And then I need to combine my like terms in the numerator. I get 44k plus 55 over common denominator 6, 4k plus 5. I do have to list my restriction though. This one's a little bit trickier because we have that coefficient in front of the k, but k could not be equal to -5/4. At this point, go ahead and pause the video, try out 43 and 44, and then resume to check your work. So I went ahead and found the answer to 43, which was 6n squared minus 12n plus 12 over n minus 1, n minus 2. I could take a GCF out of the numerator. It would not matter, though. It would not be able to factor further. Number 44, the denominator did not end up coming out like I wanted it to. This should be a -6, so I'm going to go ahead and skip that one. But just so we know, we would need to factor this denominator, see what they already have in common, and then go from there. We're going to, however, move over to the solving part. I'm going to go ahead and do one of the solvings, and then you're going to do the rest. So I'm going to go ahead and do number 46, and then you're going to try the rest of them. So number 46, that factors into n plus 3 and n plus 1. So we can see that that first fraction, it's got the n plus 3. It does not have the n plus 1. So my goal is to first get a common denominator, which now I have. I'm going to list my restrictions. N cannot be -3 or -1. Then I only care about solving in the numerator. So I'm going to distribute this 1 through. I get 1n plus 1 plus another 1 here equals 3. So I'm left with n plus 2 equals 3. To get n by itself, I subtract 2. N is equal to 1. I know that's a good solution because it does not match any of my restrictions. At this point, go ahead and pause the video, try the remaining solving questions, and resume to check your work. So the answer to number 45 was p equals 2. So again, I had to factor. This one had a GCF, and then I multiplied the first fraction by p plus 1 over p plus 1. Again, I found my two restrictions, which were 0 and -1, that if I found something that ended up being one of those restrictions, I would have to cross it off and call it extraneous. Number 47, I did have to multiply the binomials together. So again, that's that arrow trick where you draw them across from the first over to both in the second, and then the second over to both in the second. But either way, my two solutions were -6 and -3. And finally, on number 48, I factored n squared minus 25, that is difference of two squares, and then I multiplied the second fraction by n plus 5 over n plus 5. Eventually, these two, 47 and 48, these were both factoring problems. So I had to get them equal to 0, factor, and then solve. All right, finally, we're going to take a look at number 49 and then 50 and 51, but we'll go ahead and run through the key features real quick. Now, we did not talk about the graphs of rational functions in depth, but there are going to be some questions over key features, which are the same key features that we've been talking about. Now we just have to apply it to a new graph. So the first thing that we're going to start with is domain. Now, this graph will not have a negative infinity to infinity domain or range, so we got to pay attention to where things are at. So I can see that as I go from left to right, I can go all the way to negative infinity, but then I have a stopping point with this asymptote at -3. So that's my first section of domain. I'm then going to move over to the next section, which starts at -3. And then it goes all the way until this hole in the graph. Now we'll talk about that later, but if anytime there's a circle in the graph, I can't count that as a point. So it's approaching +2, but then it's that hole, so we have to stop. But then it goes to infinity. The range will be very similar. The range starts at negative infinity. It goes up until that hole at -1. Again, range is the y values. And then we start again, -1 to +1, because I go from this section up until that asymptote. And then this section will go from 1 to infinity. So thinking very similarly to our increasing and decreasing idea, wherever one section stops, the other one begins. And that's similar for domain as well. This one we do have an x-intercept. It looks like it hits about at 6, so I'm going to say 6, 0. We definitely have a y-intercept as well that happens at 0, -2. Horizontal asymptotes are next. Horizontal asymptotes always start with y equals. That's that horizontal line here that separates the function. It's where our function gets super close to but will never touch. That y value throughout is 1. The next thing we have is vertical asymptotes. Those always start with x equals. They're the ones that go straight up and down, and that x value is -3. And finally, the last thing we're talking about is a discontinuity. That's also known as a hole. So all I have to do there is list the ordered pair of that open circle on the graph, which is 2, -1. Then we're going to talk about number 51. This is related to our idea of rationals where we factor, we reduce, and we see what's left. But now we have to find the equation of the asymptote. So I know that this is going to be x minus 6 over x minus 6, x plus 4. That's how the denominator factors. These x minus 6's will go away. So what the idea of a vertical asymptote asks is that whatever factor is left over in the denominator gives us a vertical asymptote. They always start with x equals, and we flip the sign. So that graph would have a vertical asymptote at x equals -4. Number 50, we would have two vertical asymptotes. X would be at -2 and +3.